In the past, judging a science fair project, especially for new judges, can be quite daunting, especially if the judge comes from an area of expertise that's not related to the specific experiment, or maybe the judge is just a layperson who have not had any formal scientific training, but that's okay. What makes it daunting is the subjective nature of the judging. Often, what judges tend to do is judge one experiment and set that as the standard and compare all subsequent experiments to that first one. Now, if the first one was incredibly good, then it may not be fair for that first experiment because all they're receiving is an average score. Now, in an effort to kind of fix that or to improve upon that, this particular form was developed, largely modeled after some other successful science fair judging forms. And what we're doing here is separating the judging into several sections. We have the design methodology section right here, and we have the execution section and the poster section. The most obvious judging is the poster section because that's the first thing you see as a judge. And what we're looking for is a logical organization from upper left down through the middle to the lower right. And the most important information, i.e. in the case of a traditional science experiment, we want to see data and we want to see graphs. We want to see all that information down in the middle, large, proud, and prominent. For engineering, we want to see data and graph as well as iterations. We want to see that they've tried more than one attempt, that they try to improve their product, their device. So that would be the poster board section. Now, the next easiest section, I think, to judge is the design and methodology. Did they lay out their objective clearly? Did they design their experiment or design their process or their iteration of their device in such a way that they are trying to change one thing at a time and trying to do it in such a way that they can measure quantitative data or reduce the number of variabilities. So the conceiving of the experiment and or the device design process is quite critical in making the execution happen well. So this is the next section that we're gonna that would be a little more difficult to judge, but certainly not impossible. The most difficult to judge is the execution, because it involves really diving into the details of the project. And some things we're looking for in the traditional science fair projects are, well, do they have a control? That the whole purpose of the control group is really to eliminate a lot of variables that you haven't even considered. As an example, say a student is trying to investigate a certain fertilizer and its effects on a plant growth. Your control group might be just another identical plant in a pod that's identical, sitting next to the experimental plant. And maybe that control plant only gets water. Well, if that's the case, then you have eliminated all sorts of variables like temperature or time of year or the angle in which the sun hits each plant. So in effect, with the control plant, we've eliminated a bunch of variables that we may or may not have considered, which is why control is so important. Also, talking about traditional science fair projects is the number of data points that the student has. Often we see maybe 3 attempts at measuring data over 3 different times. Not a whole lot of data points and not certainly statistically significant. What that means is we just don't have enough information to make an assessment. It could just be fluke. So we would like to see a lot of data points. Now, on the flip side, you could have thousands of data points, but if you can't make sense of the data point, then they're essentially useless. So what we like to see is some kind of graph that summarizes what the data is suggesting, and maybe try to see some kind of trend. Is is the function I'm trying to investigate, is it a decaying kind of a behavior, or is it something that increases exponentially, or maybe increases linearly, or maybe there's a hump in the middle of the data that shows that there is a sweet spot in some kind of process. So while lots of data is good, but the summary of the data is actually more interesting for the science, because that tells us things that we can then extrapolate and make predictions. And when you have that many pieces of data, it's crucial for legibility, if anything else, for that data to be kind of collapsed down to, say, a set of averages instead of every single data point out of thousands of data points. Because at that point, it may or may not be legible, but certainly an average would be. And for middle school students, they've certainly visited the concept of the average, so that's something we would like to see. Now, for the engineering projects, these kind of projects, we would like to see a motivation for designing the project, and that's usually pretty easy for the students to come up with. But what we don't see often is the process, the to go from the question or the purpose that they're trying to solve to the final product. Somewhere in between, there must have had some kind of initial imagination of what this device would do, and then from there to a physical product, something has to happen, and it doesn't just blink into existence. There has to be a process where they're iterating, where they're trying things, where they're failing, and they're discovering how they can fix the thing that's failing to make it better, and eventually, over the course of many iterations, they come up to their final product. Now, that's what we want to see in an engineering project. In addition, we also want to see them do a little research on the background of the product they're trying to design. Does it already exist? And if it does, what's wrong with it that makes you want to make it better? Maybe this doohickey doesn't have this feature, or maybe they didn't consider a particular situation that you have. So that's something we would like to see in the engineering project. We don't want to see another mousetrap that looks exactly like every other mousetrap that's out there. We would like to see a mousetrap that maybe does something a little different. Maybe it doesn't kill the mouse. Maybe it does. Maybe it's easy to reset. Maybe it's extremely cheap, or very entertaining to watch, or whatever. As long as you're adding your own twist on what exists out there and you're improving upon that, that's what we want to see in an engineering project. Now, the creativity section is a little more open to being subjective. Now, this is largely a function of the experience of the judge. If a judge is highly experienced or an expert in certain scientific backgrounds, they may have seen a lot of the projects that they will be judging, and they may score lower on the creativity. Whereas on the flip side, a brand new judge who has never seen projects at the county level may find each project to be unique in its own way. So some leeway is given here, obviously, but after a few projects, even the most beginner judge would start to get a sense of the degree of thinking that's involved in planning a science experiment. Did they just simply get it off the internet, or did they really, sit down and thought about a problem and try to come up with a way to find the answer to the problem? And as a judge, Your job is to ask questions that try to ascertain this. How did they come across or come about their idea for their experiment or their device that they're engineering? And what was the motivation for that? And that gives you a sense of what the creativity is. During the interview, it's very important that the student is clear and concise and answers your questions in a thoughtful manner. What that means is they don't just say, the graph says this thing is true, therefore it's true. They must explain why the graph says it's true and what exactly is true about the graph. And if you ask them a question that's, say, maybe phrased a little bit weird, can they respond to that in an equal fashion? What's important to do is, as a judge, you have a limited amount of time to judge each project, and there are many, many projects to be judged. In order to get through all of these projects, often we don't have time to listen to a perfectly polished, pre-prepared speech. It's important that once you detect that there is a pre-prepared speech, wait for the first one or two sentences and go ahead, and it's okay to interrupt politely the student and ask them questions that are pertinent to the answers you want to get. For instance, if you wanted to see how they came up with their project, you go ahead and ask them right away, how did you come up with this project? Or you go, if you had a question about, well, what kind of variables did you try to control? Go ahead and ask those questions. Don't wait for them to give you the answers. Go ahead and ask those questions right away and see if they can give you the answers. And that usually separates the students whose projects are done by their teacher or their parents versus the students who actually went through the arduous process of doing the experiment themselves. And those are the ones we want. Now, at the middle school level, it's often difficult for students to kind of interpret their graph. So I typically give them a little bit of leeway to try to explain what's happening. But it is very important that they understand what the data is trying to say. It's very important for them to understand that the data is saying something about the question that they were trying to answer. And whether the data confirms their question or proves their question, proves their assumptions false. Either way, it's good science, but they have to use the data. And they have to understand that their experiment is designed to answer a question, and their data provides that answer. Now, if they design their experiment to answer a different question, then they have to realize that as well. This board's laid out in a fairly intuitive fashion with the motivators on the left, the data collections in the middle, and results and conclusions on the right. As a judge, I'm mostly interested in the data itself. So what I would like to see is the graphing area be less of an eye chart and more enhanced. And maybe reduction of these beautification elements here and here. Although they do fill blank spaces, I do understand that. However, they seem to kind of clutter the important part again, the graphing area. Since we're talking about graphs, let's zoom in a little bit on that. I see that these bottom three graphs here are describing the same data as the main graph up here. So for me, these are unnecessarily cluttering the presentation without adding any more information. What I would rather see is this graph expanded out to be more legible and less of an eye chart. Zooming in even further, I see that the student has graphed individual trial attempts here, 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 and so on as individual columns. And that for me is not adding information, but simply cluttering again. What I would rather see here is that the student would take the 7 trials and average them to a single number, and then comparing each of those averages per the fabrics that they've burned side by side as a comparison. I think that would be much more concise. Another thing I noticed is that the student has added his name to a panel in the upper right hand corner here. Typically that is not done because it can cause potential judging biases. So for judging, I would probably give this board an 8 out of 10. The experiment is fairly well executed. The only place where I really would take off points is that the student graphed the individual trials here, here, and here, as opposed to averaging it out. And that's unfortunate because for me, they lost a point. The way this board's laid out is very clear from the question and hypothesis what they're trying to do. They're trying to investigate the behavior of glow sticks as a function of temperature. However, in looking at the procedures, I see that they haven't really thought about how they can control the actual temperature of each beaker, because although they start off with a specific temperature, they measure the glow over a very lengthy time and over which the temperature within these beakers would have changed. So as far as design and methodology goes, I would take off a few points. Here's an interesting thing. Procedure step 10. Observe and record time in minutes when each glow stick extinguishes. Well, what exactly constitute extinguish? Glow sticks don't just turn off, they kind of get dim over time. So this observation is subjected to very high variability. And frankly, I don't know how you would do it unless you had some kind of light meter. So this particular point makes me want to take off another point for the execution of the experiment. As mentioned earlier, their measurement scale duration is in the order of minutes. So that's plenty of time for the beakers containing ice cubes to either get cooler or warmer. So there are huge sources of variability in this experiment, and those variables should have been more thoughtfully controlled, so I would take off another point for the execution. In looking at the conclusion, I see they have listed out several scenarios of what the judge or audience might want in a discrete fashion. Although this is useful and not at all untrue based on the data, it doesn't really belong in the conclusion. It really should be in an addendum section here on possibly applications of the results of this experiment. What really belongs in the conclusion panel is a summary and an interpretation of what the data means. And it really, if we look at the graph here, we see that, depending on temperature, there is a correlation of glow stick performance. So really the conclusion should have been about, well, glow sticks are affected by temperature and this is how they're affected, and we can then use that conclusion to make further predictions, and that's the whole point of the science experiment. And for that, I would take off another point. Finally, as with most graphs within the middle school category, even if they have this beautiful graph where there's an apparent curve, some kind of decay curve of the data, there is no trend line. So the trend line really gives us the ability to kind of make predictions in between the data points or beyond the data points, so we can extrapolate what the data might be if we were to take it to the extreme. And that is interesting science. That's kind of why we do this, so we can make predictions. So trend lines are very important here, especially when you have these continuous kind of functions that we're trying to describe here. So I would take off a point for not having trend line. And an additional point, students at this grade level tend to often graph every trial for their data point gathering endeavor, rather than collapsing them into an average where the data is actually more useful. So that's something to note. Moving to the poster section, I see that the panels are laid out in a logical fashion, from the motivators down to the setup for the experiment, down to the data gathering and the results interpretation. However, where I find to be kind of confusing, or at least a little bit tricky to interpret for the judge, is that the materials section and the procedure section takes such a prominent role in the center of the board. As a judge, I'm more interested in the actual experiment, which is the data and the graphs. So I would rather see these sections move to a lesser conspicuous location, say down here in a corner, and then moving these data and graph sections out to the middle, where it takes a prominent display and draws the judge's focus, and that will be the topic of most of the discussion. So for a board, I would probably take off a point or two. This poster board is laid out in a logical fashion. It has the motivators on the left, the data in the middle, leaving a little inset for procedure in the lower left-hand corner. That's okay. It's not too cluttered. And the results and conclusion all down here, maybe some additional information. The thing that really struck me immediately is the graph in the middle. Let's just simply look at one of the data sets here. I'm going to focus on this brown square, which is for boiling the solution containing bacteria. Here's a data point, here's a data point, here's a data point, here's a data point. So what the data is actually suggesting is maybe a trend line, something like this. Instead, we see a lot of very arbitrary looking trend lines out here, and I'm not quite sure where they come from. So for this data interpretation, I would take off a point. I noticed that the experimenter has listed the various ways to treat water. However, what's missing here is the control group, maybe distilled water. One would assume that the control group would show zero change over the course of the experiment. Here, the experimenter concluded that boiling is an effective way to remove bacteria. However, what they measured was not the number of bacteria, but actual pH. Now, there may be other processes that cause pH change over time, so this conclusion does not necessarily reflect the data. Additionally, the experimenter makes broad generalizations about the safeness and the taste of the water and makes a recommendation. These are not substantiated by any part of the data or the procedures, so these kinds of information do not belong in the conclusion, and I would take points off for that. Overall, the biggest problem I have with this experiment is that they measured pH, not actual physical bacterial counts. And without a control, such as distilled water, there is no way to tell that pH was caused by bacterial growth. So for the board, I would probably give this a 9 out of 10. But for execution, I would take off significant points for the lack of control and broad conclusions that do not interpret the data, and trend lines that don't agree with the data points. Probably a 6 out of 10. Projects involving the ascertaining of safety of drinking water is quite common. So as far as originality is concerned, it's about average. But because their interest is specifically the local creek, I would give it an extra point or so. So 6 out of 10. However, as a whole, the project is very clear on the purpose that it's trying to achieve. So for that, I would give the full points. Okay, here's a project that's a little more challenging. This is a high school level project, and clearly this person's working in an internship somewhere in a lab that's working on vaccines for, I guess, dengue fever. I am not a biologist by trade, so my expertise in this is very minimal. So in this case, I would consider myself a lay person. And as a lay person, I still am curious what exactly they're trying to investigate. And as a judge, who is also a lay person, I would want to ascertain more about what exactly they're trying to do and how much they've done and what kind of insights they're getting out of this experiment. So, although these types of experiments that are so involved typically have a very complex and well rehearsed presentation. But what I would like to do is immediately ask questions. Can you or can you not verbalize this purpose and what you have discovered in the data and what you draw as a conclusion in a few sentences for a layperson? In which case, once they do, I would be asking questions like, okay, so how did you find out? What tools did you use? And did the tools help you discover these kind of patterns that led to these kind of results? Now, sometimes the students are very good at explaining. Sometimes they tend to be thrown off by the fact that you're asking them such a blunt question. But it's important that we do ask these blunt questions because we want to ascertain just exactly, to be a little cynical, how much work they've actually done. Because we've had experiments in the past where it seems that their board is so well organized, yet when we ask them questions, they couldn't explain exactly what each of the sections are and what they do, which leads me to think that maybe they piggybacked off their internship and simply used the data that's there without really truly understanding the experiment or have done parts of the experiment themselves. So as a lay judge, your best effort is really to kind of ascertain their expertise in this and not just simply throwing big words at you, but can you actually explain what that means and what exactly is happening? And that's the best you can do because obviously not everyone's going to be an expert in every single subject that these science experiments are based on. So we do our best. On the subject of being an expert, some judges come in with little experience in the technical backgrounds, and other judges come in with very specific expertise in their specific areas of interest. What we find in the past during the elaboration debates for second round judging, the judges who have expertise in a particular subject tend to be more critical than the judges who don't. And that makes for an interesting discussion, but it does bring forth the question is how much bias is within a judge? And obviously being people, we can't avoid our biases. So my recommendation is really just kind of, if you're an expert, then ask the questions that ascertain whether or not this person has expertise or that they truly understand what they've done and that they drew the correct insights through this experiment. As a lay judge or someone who is not an expert in this kind of subject, your best bet is, can they explain to you exactly what they've done and how they come about doing it and what conclusions they've drawn based on the data in such a way that as a lay person, you will get a better glimpse of the subject And if they can educate you, not simply using the giant words, then that makes for a better project. So during an interview, as mentioned earlier, a lot of kids, this is their first time speaking to an adult, so they tend to have well rehearsed and practiced, memorized canned speeches. But what we need them to do is learn to explain what they've done. So the important part here is clear and concise, thoughtful response to questions, not just a canned speech, but really feel free as a judge once they've completed their first or two or three sentences explaining what their experiment is about. Go ahead and start asking questions. Ask questions about how they collected the data, ask questions about how they arrived at the conclusion, ask their questions about, well, looking at the graph, what do you see is maybe happening, and ask them questions about what kind of controls they used and why they chose those controls, what kind of variables those controls are trying to eliminate. Those are very important questions that ascertain their level of understanding of the experiment and their insight to the results. Plus, it gives you a little bit of a glimpse of their understanding of the basic science behind the experiment, as well as engineering any kind of equipment that's required for the experiment. On the subject of equipment, it's okay if parents or other people, grown-ups, or even professional labs help you create your apparatus by which you run your experiment. However, it is not desirable for someone to rely on those other external help to actually do the experiment. The idea is that they do their own experiment, even though the equipment might be manufactured by a helpful parent or a professional source. For the third point, the quality ideas for further research testing. This really is a set of questions you ask during the interview to ascertain whether they have gained insights. Now, it's okay that they've run an experiment and come to a conclusion, and that's it. But for the projects that really could go on further and have more potential, it's those students who not only ran their projects, but through the process of running their experiments, really discovers more and discovers enough insight to ask further questions and maybe realize that maybe there are certain aspects of their experiment that they can change to come out with better data or data that answers a different set of questions. So these are very important questions to ask. As well, at the same time, the student also would be answering and showing you their interpretation and their understanding of the limitation of their particular experiment. Now, in the case of engineering projects, it is crucial that the manufacturing of the project is done by the student, because this, unlike a traditional science fair project where you're trying to investigate something and you might need equipment that is being built by someone else. But in the case of engineering, the whole purpose of this is to design and build a piece of equipment or a device or some kind of process. So having a lot of external help here is not desirable and kind of besides the point. On some occasions, as a judge, you will encounter projects that are done by several students collaborating together. In those cases, almost never is the division of labor perfect, but that's okay, as long as each of the students understands the project from start to finish, as long as they can all answer questions about how the process was run, and they all are able to kind of verbalize the insights that are needed to draw the conclusions that they drew. And that your job as a judge really is to kind of ask questions to each and every one of the members, maybe not the same questions, but certainly enough questions to ask each person to ascertain whether they've had at least a significant effort in the experiment. Occasionally, you get teams where one person does all the work and everyone else gets the credit, and clearly for those projects, we would deduct points. Finally, at the bottom, we have this section. So what this section is for, to me, is while you can have a project that checks all the boxes on the judging sheet and follows all the rules, and yet is just not enough to go on. What do I mean by that? Say you have a project. Let's say someone's doing potato clock or potato battery. That project has been done a million times by almost every middle school kid in the country. Now, that said, originality is probably not great. But if they had followed all the correct scientific methods, they laid out their board perfectly, they collected excellent data, they would get very high marks on the judging sheet. However, is that project worthy of moving forward to the next level? Probably not, because it doesn't have the kind of originality or the kind of interesting nature to the project that gives it the potential to go further. And what else do you do with a potato battery? You can string them in series, you can string them in parallel, but ultimately it's just a set of potato batteries. And there's not much more you can explore or investigate beyond that. So moving to the next level, the next round of judging, we would expect more out of it and more in-depth investigations. And in the case of the example, the potato battery, there is just no more potential there, or very little. So we would say, well, probably not for that. Now, on the opposite end of the spectrum, you might have a project that, maybe didn't follow all the rules for how the board's laid out, or maybe didn't miss the trend line on the graph, or kind of missed a particular variable that they should have considered. But that project may be so interesting that if you just tweaked it a little bit, that project would be so much better. And for those cases, I would tend to say yes for that. So it is really to the discretion of the judges. And ultimately, from a statistical standpoint, when all the judges' choices are tallied in, there will be typically a breakdown of what projects that really want to move forward. And so every little input is going to be considered.